here is the first surprise: you can't. Not because our engines are too weak, but because the universe will not allow it. Anything with mass, a spaceship, a person, a single atom, can get closer and closer to the speed of light, 90%, 99.9, but never reach it, because the energy required climbs toward infinity at the finish line. And yet the closer you get, the stranger reality becomes. Time nearly stops for you. The entire universe ahead crushes into a single blinding point of light. And a round trip toward a distant star could set you down thousands of years in the future, still young. So let us do the impossible carefully. What would actually happen, step by step, if you pushed yourself toward the speed of light? Start with the wall, because it is the rule that shapes everything else. Light in a vacuum travels at almost 300,000 kilometers every second, a number physicists simply call c. Einstein's special relativity, published in 1905, says c is not merely the speed of light, it is the maximum speed of cause and effect, the fastest anything in the universe can influence anything else. To push an object with mass faster, you have to add energy, and relativity's real equation, E equals gamma mc squared, hides a trap. That gamma factor grows without limit as you approach c. At 90% of light speed, you are only a bit harder to push. At 99.99%, each tiny gain in speed demands an outrageous surge of energy, and to actually touch c, you would need an infinite amount. There is not infinite energy in the universe, so the door stays shut. Note the careful version. It is not, as the old textbook said, that you gain mass. It is that the energy needed to accelerate you runs away to infinity. The result is the same. Light speed is a wall you can sprint toward forever and never cross. Now the part that sounds like fiction and is simply true. As you approach that wall, your time slows down relative to everyone you left behind. This is time dilation, and it is not an illusion or a trick of the clocks. It is the rate of time itself changing. The faster you move through space, the slower you move through time. At everyday speeds, the effect is invisible, billionths of a second. Near light speed, it becomes enormous. Imagine a ship that accelerates at a steady, comfortable 1 gravity, so you feel normal Earth weight the entire way. After about a year of this, you are traveling at a large fraction of c, and the clocks begin to diverge wildly. By your watch, 20 years pass, and you have crossed 170 light years. But back on Earth, roughly 340 years have gone by. Stay aboard for 30 years of your life, and you could cross more than 2,000 light years, while 45 centuries pass at home. You are not traveling faster than light. You are traveling so fast that time and distance themselves bend to let you through. That is the genuinely staggering consequence. Relativity hands you a one-way time machine to the future, free of charge. Fly fast enough, for long enough, and you can step out a few months older while everyone you knew has been gone for centuries. The universe will have aged. You will not have. And there is no paradox here, nothing speculative. This is tested physics. We see it in particles called muons, made high in the atmosphere, that should decay long before reaching the ground, yet survive the trip because they are moving so fast their internal clocks run slow. We account for it in the GPS satellites overhead, whose speed makes their clocks tick at a measurably different rate from ours. Speed really does buy you time. Just not in any direction you can spend. So that is what would happen to your clock. What would you actually see out of the window? Not the calm starfield of the movies. As you accelerate, an effect called aberration sweeps the whole sky forward. Starlight that was off to your sides, even behind you, appears to swing around toward your direction of travel, until the entire universe is crammed into a shrinking circle dead ahead. At the same time, the Doppler effect shifts the color of that light. The stars rushing toward you turn blue, then violet, then blaze up into invisible ultraviolet and X-rays, while everything to the rear stretches red and fades to black. Near light speed, the view collapses into a single brilliant blue-white point directly in front of you, ringed by darkness, the rest of creation switched off. You may have heard this called a starbow, a pretty rainbow ring of stars. That is the storybook version, and mostly a myth. The real view is stranger and lonelier, a tunnel narrowing to one searing eye of light. And here is the elegant twist that makes the time travel arithmetic work. From your seat, you are not the one who is strange. It is the universe that has changed. In your frame, space itself contracts in the direction you are moving. The distance to your target star shrinks. A journey an Earth observer measures as 100 light-years might, from inside the ship, be only a few light-years across, which is exactly why you can cross it in so little of your own time. You and the Earth will disagree about how much time passed and how far you traveled, and relativity's quiet miracle is that both of you are completely right. There is no master clock and no true distance. Speed reshapes them both. Push all the way to the edge to see itself, and physics does something revealing. It stops answering. People often say that from light's own point of view, no time passes at all, that a photon born in a distant galaxy arrives at your eye in what feels, to it, like a single instant across billions of years. It is a beautiful idea, and you will hear it everywhere. But strictly, relativity forbids it. There is no valid point of view at the speed of light. The equations that let us hop between moving observers break down, dividing by zero, the moment you try to ride a beam of light. A photon does not experience no time. It has no frame in which to experience anything at all. That is not a gap in our knowledge so much as the universe telling us the question is malformed. Light does not crawl through time. Light is, in a sense, what time is measured against. What about going faster, past the wall entirely? Here we leave tested ground, and it is worth being honest about where that line is. Physics allows a few loopholes on paper. There are hypothetical particles called tachyons that would always travel faster than light, but none has ever been detected, and they would let effects arrive before their causes, unraveling the order of events. There is the Alcubierre drive, a genuine solution to Einstein's equations that moves a bubble of space rather than the ship inside it, sidestepping the barrier, but it demands a kind of negative energy we have never found and may not exist. These are not predictions. They are the field's careful daydreams, the places where the equations leave a door slightly ajar. So far, every experiment ever run says the wall holds. So what would happen if you traveled at the speed of light? You can't, and the reasons you can't are stranger and more beautiful than the trip would be. Chase it and you would watch the universe fold itself up in front of you, your clock falling silent while centuries poured past outside, the whole cosmos compressed into a single point of blue fire. The closest we have ever come is inside particle accelerators, where we drive protons to 99.9999% of c, fast enough that they age tens of thousands of times more slowly than we do, and still not one of them has ever reached the line. Light keeps its lead, always, by an infinite margin. Because the speed of light was never really a speed limit, like a number painted on a road. It is the seam that binds cause to effect, the rate at which the universe allows one moment to become the next. You cannot catch light. Light is how everything else keeps time.